Um, so shall we start now?
Yes.
Okay. Ladies and gentlemen, welcome to join the PolyU Civil and Environmental Engineering webinar series, which is co-organized with the Hong Kong Institute of Engineers Civil Division, with the title Halogen Chemistry and Implication for Air Quality and Climate. Today, we are very happy to have Dr. Qian-Jie from the Department of Civil and Environmental Engineering of the Hong Kong Polytechnic University to give us the presentation. Dr. Chen is an assistant professor working on the atmospheric environment at the Hong Kong Polytechnic University. He obtained his Bachelor of Science in Atmospheric Science from Qian Zhongshan University in 2011. Also a Master of Science in Physics and Climate Science from the Utrecht University in 2013. And afterward, he obtained a PhD in Atmospheric Science from the University of Washington, Seattle in 2017. He served as a postdoctoral fellow at the University of Michigan Ann Arbor from 2018 to 2020. Dr. Chen's research focused on air pollution and climate change, including tropospheric halogen, sulfur, and nitrogen chemistry, as well as atmosphere-psychosphere interactions. He employs a variety of research tools, such as the numerical modeling with the GeoChem Global Chemical Transmodel, field observations with chemical ionization mass spectrometry, and laboratory measurements with isotope ratio mass spectrometry. He was a selected participant in the 15th Atmospheric Chemistry Colloquium for Emerging Senior Scientist SS15 in 2019. So it is time to give the stage to Dr. Chen for his presentation. Thank you.
Okay, thank you. Am I supposed to speak now?
Yes,
yes.
please.
Okay,
The
thank
stage is
you.
yours. Thank you, Dr. Chen.
Yep. So thank you for the opportunity to give a talk here. And hello everyone. I am Qian-Jie from PolyU Department of CEE. So let me first give a brief introduction of our department, CEE. So our department has global recognition. 26 CEE scholars rank the world's top 2% scientists. And many majors in our department rank #1 in Hong Kong, actually. So the civil and structural engineering ranked #14 globally, civil engineering #3, transportation science and technology #2, and environmental science and engineering #47. We have one member of the Chinese Academy of Sciences, 7 Qian-Jie scholars, and 1 fellow of Australian Academy of Engineering and Technology, and 1 fellow of Royal Academy of Engineering of UK. And over the past 7 years, we've got 4 TRS projects funded, theme-based projects, to work on intelligent tropical storm resilience system for coastal cities by Professor Lin Yiqing, unraveling the black box between air pollution and public health for transformative air quality management by Professor Li Xiangdong, and sustainable marine infrastructure enabled by the innovative use of seawater, sea sand, concrete, and fiber reinforced polymer composites by Professor Tang Jingguang, and photochemical air pollution in highly urbanized subtropical regions by Professor Wang Tao. CE also got many projects funded from Green Tech Fund, the Lentil Conservative Fund, the Collaborative Research Fund, RGC, and CRF, and the Research Impact Fund, RGC-RIF. We have undergrad program in civil engineering, environmental engineering and sustainable development. We also have a master program in civil engineering and environmental management and engineering. And we also have MPhil and PhD programs. We have many outstanding alumni, including Professor Choi Gin-Kyun, who is the past president of Hong Kong IE. We have 30 laboratories, 2 workshops, and 1 research center in Shenzhen. So we have really good facilities. And so feel free to check out the website and our CEE newsletter, and also the social media channels, and stay connected with CEE. Okay. Now, I'm going to talk about our recent research on halogen chemistry and implications for air quality and climate. Okay, so halogen atoms, such as chlorine, bromine, iodine, they have 7 electrons in the outermost electron cell. That means they are really strong oxidizers. And in the atmosphere, we are more interested in the chlorine, bromine, and iodine species rather than the other halogen species. The chemical bond strength decreases from hydrogen fluoride to hydrogen iodine. So the fluorine atoms, they can react really fast with water to form HF, hydrogen fluorides. And therefore, they cannot react in catalytic cycles. So they are not that interesting in atmospheric chemistry. HCl bond strength is similar to that of the organic carbon-hydrogen bonds. This allows chlorine atoms to react with hydrocarbons and ozone. Bromine atoms are less reactive to hydrocarbons, and most often they react with ozone or aldehydes. And then the iodine atoms are even less reactive, and they react mainly with ozone. The astatine and tellurine do not occur in nature, and they are radioactive. And in this talk, we mainly focus on chlorine and bromine species. So reactive halogen chemistry is very complicated. There are so many halogen species in the atmosphere, and this is a bromine as an example. So for example, and there are many halogen reactions going on in the atmosphere as well. So for example, the HOBr, these bromine species, they can react with chloride and bromide on the sea salt aerosols to produce Br2 and BrCl, which can then photolyze to produce bromine radicals. Bromine radicals or bromine atoms can also be produced from the organobromines released from the anthropogenic and biological activities. These bromine atoms can react with ozone to produce BrO. BrO can then photolyze or react with NO to produce Br radicals again. BrO can also react with HO2 to produce HOBr, which can photolyze to produce Br radicals. And in clouds, HOBr can oxidize dissolved sulfur dioxide, so sulfur 4, bisulfite, and sulfite to produce sulfate. Okay. And BRO can react with NO2 to form BrNO3. Br can react with BrNO2 to form BrNO2. Okay. And Br can also react with formaldehyde and acetaldehyde to form HBr. So I'm just showing this to show you that reactive halogen chemistry is really, really complicated in the atmosphere. And there are so many reactions going on in the atmosphere of reactive halogen. Okay, but they are very important. Okay. So for example, it is well known that halogen chemistry can cause ozone depletion or ozone loss in the stratosphere, so 20, 30 kilometers higher up in the atmosphere. It creates an ozone hole over the Antarctica. Okay, and a Nobel Prize was awarded to these ozone halogen topics in 1995. Okay, for their work concerning the formation and decomposition of ozone. And halogen is also important in the troposphere, so the lower atmosphere. It can remove tropospheric ozone, which is a greenhouse gas. And when ozone decrease, then the OH decrease. Okay. And this will affect the lifetime of methane, which is also a greenhouse gas. And when OH decrease, the aerosol abundance decrease as well, so including the sulfate, nitrate, and organics. So from a previous study, the reactive halogen chemistry has a net cooling effect on the climate system, but with really large uncertainties because we really don't know how much reactive halogen species are there in the atmosphere. In the relatively polluted atmosphere, for example, in Hong Kong and in mainland China, when we have a lot of chlorine radicals or chlorine atoms, they react really fast with VOC species, so volatile organic compounds, to produce secondary organic aerosols, SOA, and RO2 radicals. And these RO2 radicals can further form more ozone and HO2, OH, and sulfate and nitrate aerosols. Okay, so the reactive halogen chemistry can really cause bad air quality in Hong Kong and mainland China. And we don't really know how much reactive chlorine species there in China. And the formation mechanisms of ClNO2 and Cl2, which are the main source of Cl radicals, are not well understood as well. Okay, and this is a global anthropogenic chlorine emission flux. And we can see China is a hotspot of anthropogenic chlorine emission. Okay, other regions with high anthropogenic emissions include Southeast Asia, India, Central Africa, and Europe. And as a result, the PM2.5 chloride concentration in China is pretty high. So it can reach up to 10 microgram per cubic meter during winter in North China and Northeast China. So PM2.5 chloride alone can already exceed the WHO guideline of about 5 or 10 microgram per cubic meter. The anthropogenic chlorine sources include coal combustion, biomass burning, waste incineration, and wastewater treatment. And our research are related to many aspects of reactive chlorine chemistry. For example, the abundance of reactive halogens in China and globally. So we focus on Cl2 and ClNO2 species. So these are the two species that are most important for the CR radical production in China. And we also explore the chemical formation mechanisms of reactive halogens, reactive chlorine, and we focus on heterogeneous chemistry on aerosols and aerosol photochemistry. And then we evaluate the impacts of reactive halogens on the atmospheric oxidative capacity, the air quality, and climate. Okay, today I will mainly talk about three recent projects that we are working on. So project number one, the field campaign in Northeast China to measure reactive chlorine species. Project number two, the iron-3 chloride aerosol photochemistry to produce CO2 into the atmosphere and impacts on air quality. And then I will also talk about the sulfate production from reactive halogens in Hong Kong. We've done some isotopic measurements. Okay, so this is the global chlorine radical concentration distribution. So chlorine radical is really the key of reactive chlorine chemistry because it can react with hydrocarbons really quickly. Okay. So you can see that the chlorine radical concentration is on the order of 10 to the 3. So this is really low concentration compared to OH radical. So that's 2 orders of magnitude lower than the OH radical concentration. At such low concentration, we are not able to measure the chlorine radical concentration in the atmosphere. Okay. But we can then instead measure the concentration of the Cl radical precursor, for example, Cl2 and ClNO2. Okay, so these are the model results generated by our group member, Zhao Wenjia. Okay, so for the field measurements, I and my group have been involved in 3 field campaigns, so including the Booth Bay measurement field campaign in Northeast US in January 2019, the Guangzhou campaign in November, December 2022, so 2 years ago, and the Changchun field campaign in January to March 2014, so that just the previous winter. We used the chemical ionization mass spectrometer, SIMS, to do the reactive chlorine measurements. Okay, let me talk about the field campaign in Changchun first. So this is the motivation of this project. We still have pretty high PM2.5 concentration in Northeast China during winter. So there are still haze events. The PM2.5 concentration can reach up to 100 microgram per cubic meter during the haze episodes. Okay, so it can reach, for example, 250 microgram per cubic meter during haze episodes in Jilin. And this is because so in Northeast China during winter it is really cold. So the temperature it's about -10, -20 degrees Celsius, and so there are a widespread household heating that release a lot of air pollutants into the atmosphere. And the PM2.5 concentration increase during the haze events from the previous studies. And then we were thinking that, and we are also very curious that reactive chlorine chemistry could be important during the haze formation in Northeast China, because we saw an increase in the chloride aerosol concentration. Okay, and typically in Northeast China during winter, the ground is covered by snow. Okay, really cold environments. So this is really different compared to the atmospheric environment here in Hong Kong. And the ground snowpack can create a stable boundary layer, which can then trap the air pollutants. And it can also produce high albedos, so we can have strong photochemical reactions in the atmosphere. And there are the snowpack can serve as a surface for heterogeneous reactions and photochemical reactions to release trace gases into the atmosphere. For example, to release CO2, release HONO, so nitrous acid, and release ClNO2 into the atmosphere. So these are the three important trace gases to produce OH and Cl radicals in the atmosphere. So Cl and OH radicals are really strong oxidants in the atmosphere. They remove a lot of things in the atmosphere, and they produce secondary organic aerosols as well. Okay, so then from the model results, we can see that Northeast China is a hotspot of PM 2.5 chloride, a lot of PM 2.5 chloride there. During the field campaign, air temperature is really low. The ground is covered by snow. We put our instruments inside this trailer, so to keep it warm, so it can walk well. And then we have an inlet outside the trailer wall, so we can suck the air into our instruments. And we also use a sonic anemometer to measure the three-dimensional wind speed, so we know the turbulence conditions. And we also collect PM 2.5 and snowpack samples, so we can use them to do further chemical analysis in the lab. And in this field campaign, we measure ClNO2, CO2, N2O5, and HONO. We perform not only ambient measurements, but also vertical profile measurements. So we measured the concentration at different heights above the snowpack. We did the background measurements every 30 minutes, calibration every hour. So we make sure that we can have high quality of the data. The detection limit of NO2, CO2, and N2O5 are typically below 5 ppt with 20% uncertainty, and HONO is about 80 ppt and LOD. Okay, let me show you some results. So this is the CO2 diurnal profiles of CO2, NO2, and N2O5, and temperature and relative humidity. So for ClNO2, and you can see the green line here. Okay, the concentration is pretty high. It can be about hundreds of ppts. So the maximum is about 1.5 ppb. So 500 ppt. So this is pretty consistent with our previous observations in other regions of China and also Hong Kong. So in that region, a lot of chloride and a lot of ClNO2. And very interestingly, we observe an increase of ClNO2 after the sunrise. So typically, ClNO2 concentration will decrease after sunrise. It is produced at night from the reaction of N2O5 with chloride on aerosols, and then typically it decreases in the morning, so upon sunrise, because it can photolyze really quickly. But we saw it keep increasing after the sunrise for 2 or 3 hours. Okay, and this is because we have a downward transport of the high ClNO2 from the residual layer, and this is really a typical case, typical phenomenon, a pretty interesting phenomenon in Northeast China. So this is the first ClNO2 and CO2 observations in Northeast China. So we conduct vertical profile measurements to obtain the air-snow surface exchange flux of these 4 species, and I'm showing some examples here. So the y-axis, that would be the height. So on the x-axis, that's the concentration. For example, for cell NO2, we can see in the concentrations higher or lower at the surface and higher at about 1.5, 1.8 centimeter. Okay, so that indicates at deposition, a downward flux of Cl2 toward the snowpack. But then we observe an emission of Cl2 and HONO during daytime. Okay, we observe higher concentration of Cl2 and HONO at the surface compared to the upper air. And this is really interesting results, and we are planning to implement this kind of flux into the GeoScan model to see a broader impacts on the air quality in Northeast China. And we compare the production rate of Cl radicals from Cl2 and ClNO2, and we can see that Cl2 is a larger source of chlorine radical than ClNO2. So the red line is for Cl2. Even during the morning when we have high ClNO2, maximum ClNO2 concentration, the contribution of Cl2 to the chlorine radical production is comparable to that of Cl2, of ClNO2. So Cl2 is really important in our relatively polluted environment in China and also Hong Kong, actually. And then we compare the OH production rate from HONO and from ozone. Then we can see that, well, the magnitude between for HONO and ozone are very different. So we can see that the HONO is a factor of 100 larger than ozone in terms of OH source. And if we compare the production rate of chlorine and production rate of OH radicals, then we can see that production rate of OH radicals is about only 20% of OH radicals. So if we assume a photochemical equilibrium for Cl and OH radicals, then the production equals the sink, then we can see that OH is more important than chlorine in terms of atmospheric oxidative capacity. So we also conduct a few campaigns in Guangzhou 2 years ago, and we observed much lower ClNO2 and Cl2 concentrations. I don't have time to get into that. So in Guangzhou, that's a forest site. Okay, so it kind of better represent the background concentration, background ClNO2 and Cl2 concentration in the Greater Bay Area. Okay, next, then I will talk about the chemical formation mechanisms of Cl2, because Cl2 is such a big source of chlorine radicals in the atmosphere. And I will talk about the iron chloride aerosol photochemistry to produce Cl2. Okay, so in the atmosphere, we have iron 3, we have irons, and we have chloride, and they mix together in aerosols, and under sunlight conditions, they will undergo photochemical reactions to release Cl2 into the atmosphere. Okay, so actually, we don't have a good understanding of Cl2 formation mechanisms in the atmosphere, although it's really important for the Cl radical production. So with the up-to-date gas phase and multi-phase reaction to produce Cl2, the models still cannot reproduce the observations of Cl2. So for example, the GeoScan model cannot reproduce the 2 ppb of Cl2 observed during the winter flight campaign over eastern United States. And we use a box model to analyze the Cl2 formation in Nanjing. And you can see that black dots are the observations, and the blue line is the model results. So the model really underestimates observations a lot. Okay, we have a really poor understanding of the CO2 formation mechanisms. And we further analyze the correlation between the mixing source of CO2 and the sunlight conditions. So in this case, photolysis frequency of NO2, and also the surface area of aerosols and PM2.5 concentrations. And they correlate pretty well. So we propose that the mixing source of CO2 is due to some aerosol photochemistry that produce CO2. And actually, the isotopic signals of CO, carbon monoxide, observed in the North Atlantic also implies methane oxidation by Cl radicals. So they proposed that Dutch aerosols from Sahara Desert can mix with the seesaw aerosols to produce CO2 through iron-induced aerosol photochemistry. And CO2 was observed to be produced from these iron chloride containing aerosols in the smoke chamber experiments, and they measure the CO2 production rate in the chamber experiments that we can use for our models. And also, the previous study has used aqueous equilibrium model to simulate CO2 production from the iron-3 chloride aerosol photochemistry. So this is also recent work. So in this study, we implement this new CO2 formation mechanism. So this iron-3 chloride aerosol photochemistry into the GeoChem global chemical transport model. So the nested version of the model has a resolution of about 0.3 degree, and we have anthropogenic chlorine emissions added into the model. So we have anthropogenic chlorine emissions from coal combustion, industrial processes, biomass burning, and waste incineration. In the model, we also simulate aerosol iron. So aerosol iron can come from dust. So it can be 3.5% of the mass of the dust, 4% solubility. Aerosol iron can also come from anthropogenic source. So the anthropogenic aerosol iron is about 1/30th of the primary sulfate emission flux in the model, okay, with 40% solubility. And in the model, we do iron speciation as well. So iron-3 accounts for 67% of the soluble iron in the model. And then we implement these reactions into the model. So CO2 production rate is proportional to photolysis frequency of NO2, the iron-3 concentration, chloride concentration, and aerosol surface area. So the scaling factor alpha is based on previous chamber experiments. And then during our modeling period in December 2017, we have PM2.5 chloride observations at 29 sites in North China. And that's why we picked that modeling period. And in general, the model reproduced the observed PM2.5 chloride concentration pretty well. So the observed PM2.5 chloride concentration is 5.6 microgram per cubic meter, and the model result is about 8.3 microgram per cubic meter. So it's really not usual to model the chloride concentration in the model. So our observations are pretty well already. And our model reproduced the daily variability of PM2.5 chloride And when the chloride concentration was overestimated, the PM 2.5 was also overestimated. So the overestimation of PM 2.5 chloride is likely caused by the mixing scheme in the model and also some meteorological condition in the model. Okay, and then this is for the model observation comparison for the aerosol total iron. And in general, the model reproduced pretty well with the observed aerosol total iron. So the observed aerosol total iron concentration is 1 microgram per cubic meter, and our model value is 0.9 microgram per cubic meter. And the daily variability was pretty well reproduced as well. And the iron solubility in the model is also pretty consistent with the observations. So during that sampling period, we have aerosol iron solubility observations at 2 sites in North China, so in Beijing and also in Handan. Okay, let's see some impacts on the CO2 and reactor chlorine budget. So before we add any reactions into the model, before we add this new mechanism into the model, the CO2 mixing ratio is typically less than 1 ppt over North China, okay, with an error range of only 0.5 ppt. And the biggest source of CO2 is the reaction of OH with chloride on aerosol particles. Okay, but then after we add this new mechanism into the model, you can see that the CO2 mixing ratios increase to 5 ppt. So that's a huge increase of CO2 in the model. And now the biggest source of CO2 in the model is from iron 3 induced aerosol photochemistry. And then we compare our model results with the observations observed at the Wangdu site in December 2017. So the black line are the observations, and the blue line is the model results without or before we add the new mechanism, and the red line is the results after we add the new mechanisms. We can see that the model performed much better for the CO2 simulation and for the diurnal profile as well. So before we add this mechanism into the model, during daytime, the model over observed CO2 value is about 1/83. And during nighttime, it's about 1/96. So that's a really large discrepancy between the model and the observed CO2 levels. And after we add this reaction into the model, during daytime, the model result over the observation is only 1/3, and during nighttime is 1/2. Okay, so the discrepancy between the model and observations has been largely decreased because of these new mechanisms added into the model. How about the impacts on the radicals and air quality? So we see that the chlorine radicals increased by a factor of 20 to 40. So really large increase in the chlorine radical abundance. So that's a factor of 20 to 40 in the regions with really high concentration of aerosol iron and aerosol chloride. And before we add the model, before adding the new mechanism into the model, ClNO2 is the biggest chlorine radical source, accounting for 83% of the Cl production, and CO2 11%. after we add the reaction into the model, Cl2 becomes the biggest source of Cl radical, so accounting for 65% of Cl radical production, and ClNO2 32%. Okay, by adding this reaction into the model, the OH concentration increased by 9% on average, and in some regions it can reach 20 to 40%. And the VOC reactivities increased by a lot as well, because the chlorine radicals can increase, can react quickly with VOC radicals, and also the OH radicals concentration increase. So the VOC reactivities also increase. And the OH concentration, the OH abundance increased by about 10% on average. The PM2.5 concentration increased by 3%, and that's mainly due to nitrate. So we didn't evaluate the impacts on the secondary organic aerosols in this work, and that should be done in the future. There are a lot of uncertainties of these new mechanisms. So, for example, the aerosol iron, for aerosol iron, the soluble iron is underestimated by 31% in Beijing and overestimated by 69% in Handan. And the iron 3 solubility speciation is also uncertain. So you have 12% certainty. The aerosol chloride is overestimated by 50%. The aerosol surface area concentration is overestimated by a factor of 3 in Wangzhou. And we use photolysis frequency for JNO2, which can be different from the iron 3 chloride complex. And we didn't consider the influence of sulfate and organics. So these the sulfate can form a complex with iron 3, and that decreases the iron 3 chloride complex. The organics can remove the OH radicals, Cl radicals, and Cl2 minus radicals in the aerosols as well. And we didn't consider aerosol acidity in this work, and this is really important. Aerosol acidity can really affect the speciation of iron and what complex it can form in the aerosols. Okay, and we also did some lab experiment to investigate the CO2 production from the aerosol uptake of ozone. So we have a flow tube in the lab that we inject ammonium chloride aerosols and ozone into a flow tube to measure the the uptake coefficient of ozone by these ammonium chloride aerosols. And we found that the results are pretty consistent with our observations in Guangzhou. Okay, our group member Han-Shi Chen is working on this. Okay, next I'm going to talk a little bit more about the impacts of reactive halogens. So the sulfate production from reactive halogens in Hong Kong. Okay, sulfate. Sulfate is really important for air quality and also climate. So sulfate is hygroscopic, so it can take up water and from the ambient atmosphere, so that particles can grow. They can grow bigger, and then form the haze. Sulfate aerosol can also cause acid rain and cause damage to the ecosystem, to the sculpture, and to the buildings. Okay, in Hong Kong and our Hong Kong PRD region, sulfates account for about 30% of the PM2.5 mass. Sulfate is also important for climate, so it can nucleate, it can scatter radiation back to space directly or indirectly by forming cloud droplets. So one of the geoengineering projects to cool the Earth is by injecting sulfate aerosols into the atmosphere to mimic a volcanic eruption. So from the IPCC report, we can see that SO2 and sulfate aerosol has a really large negative radiative forcing, but also with large uncertainty. And it's really important to understand sulfate formation in the marine boundary layer because the albedo of the ocean is really low. So if we have aerosols or we have clouds above it, that can have a large impact on the climate. So sulfate, how does it form? It's produced from oxidation of sulfur dioxide. So sulfur dioxide can react with OH radicals to form a sulfuric acid, which can nucleate new particle formation in the gas phase. Okay, sulfur dioxide can also be dissolved in the cloud droplet to form sulfur 4, which can then be oxidized by hydrogen peroxide, ozone, and catalyzed TMI, ozone, oxygen. So by oxygen catalyzed by trace metals, and HOCl, HOBr, HOI. So hyperhalous acid. And while DMS, dimethyl sulfide, can emitted from the ocean, they can also undergo chemical reactions in the atmosphere to form MSA and then sulfate aerosols. But this is not important in Hong Kong. Okay, in Hong Kong and the nearby regions, there could be a lot of reactive halogens there. It's HOCl, HOBr, and HOI. So HOCl was measured to be 10 to 100 ppt at coastal Hong Kong. And HOBr was too low to be observed, so it has a concentration of about 0.1 ppt in the model. HOI has a concentration on the order of 1 ppt. Okay, from a previous box modeling study for coastal city, HOI accounts for 57% of sulfate formation, and hydrogen peroxide accounts for 30%. As I'm going to show you soon, so this is pretty consistent with our isotopic results. So we did a field campaign at coastal Hong Kong in 2021. So during the campaign, the Hong Kong site, Hock Choi, received air mass, clean air masses from South China Sea, and also relatively polluted air masses from southeast coast of China. And during the campaign, we connect PM2.5 samples to measure the sulfate oxygen isotope composition. And also we have SIMS, chemical ionization mass spectrometer, to measure reactive halogens. So the SIMS can measure HOCl pretty well, as you can see from this isotopic plot for HOCl. Okay, I'm going to skip that. And then for and then we sent our PM2.5 samples to University of Washington in Seattle for sulfate oxygen isotope measurements. So Alison Moon from University of Washington did the analysis for us to dissolve the filters and separate the sulfate ion, and then to convert it to silver sulfate and measure the oxygen 16, 17, and oxygen 18 for the sulfate. So sulfate produced from different mechanisms can have a different isotopic signature. That's why we use isotope measurements to do this kind of to investigate the sulfate formation mechanisms. So for example, sulfate produced from OH, TMI oxygen, and HOX, so that's hyperhalous acid, has O17 excess of what we call the capital delta 17O value of 0 per mole. Okay, And if that's produced from hydrogen peroxide, it has an O17 excess value of 0.7 per mil. So capital delta 0.7 per mil. And then if that's produced from ozone oxidation, the capital delta 17O of sulfate is 9.8 per mil. Okay, they're very different. And during our sampling period, the delta 18O of rainwater was also measured in Hong Kong. So this allows us to have more isotopic constraint on the sulfate formation mechanisms. And these are some the observed O17 excess of delta 17O value and delta 18O values for our samples. And we saw actual really low values in our samples. And from that, we can calculate the ozone contribute at maximum 7% for sulfate formation. And hydrogen peroxide contribute at maximum about 30% for the sulfate formation. And from the delta 18O value, that also show pretty low O7 delta 18O values. And it's very different from compared to the primary sulfates emitted from the ship and from the vehicles. So the air pollution control policy in China could have effectively reduced the primary sulfate emissions from both the land and ship-based anthropogenic fossil fuel combustions. And then we did the calculation and to calculate the fraction of sulfate produced from hydrogen peroxide and hyperhalous acid and other pathway. I'm showing it here as a ternary plot. And we can see that for 7 out of 12 case days, hyperhalous acid contributes more than hydrogen peroxide to sulfate production. And for the rest 5 cases, it's probably that hyperhalous acid HOX is more important than hydrogen peroxide for sulfate formation as well. And if you use the median value, that we can see the hyperhalous acid accounts for 48% of sulfate production in coastal Hong Kong. Okay, hydrogen peroxide accounts for only 14%, and the other pathway accounts for 38%. And does it make sense though? Then we use a box model to calculate sulfate production with the best estimate of the oxidant levels. And we obtain the results that hydrogen peroxide, for the clean air mass, the hydrogen peroxide accounts for 23% of sulfate production, and HOI 31%, HOBR 9%, HOCl 20%. Ozone only 2%. And in the polluted environment, hydrogen peroxide accounts for 11% of sulfate production, HOCl 63%, 4% for HOBR, and 14% for HOI. Okay, so from the box model results, we can see that halogen, reactive halogens, so hyperhalous acid, are more important than hydrogen peroxide for sulfate production at coastal Hong Kong. So this is consistent with our isotopic calculation. Okay, to conclude, from these 3 projects, we found vertical mixing and snowpack are important for reactive chlorine. The iron-3 chloride aerosol photochemistry is the dominant source of Cl2 in North China during winter, and the isotopic evidence shows high contribution of HOX, hyperhalous acid, to sulfate aerosol formation in the coastal marine boundary layer in Hong Kong. Okay, with this, I would like to thank the RGC and NSFC and PolyU for the funding. And I also want to thank the co-authors and our group members. Okay, thank you very much.
Thank you, Dr. Chen, for his comprehensive presentation regarding the field measurement, the laboratory as well as the modeling for those reactive halogen species. So now it comes to our Q&A session. For those participants who have questions, you are feel free to use the chat box to type your question here or use the Q&A box as well. So in the meantime, maybe let me have the first question to Dr. Chen first. I can see that you have experiment or the study regarding the reactive halogens in Hong Kong or the formation and the chemical reactions. So how is actually the general situation in Hong Kong for the halogen formation, and also how can the Hong Kong government can improve the air quality or to improve the air to mitigate the air pollution by using different chemical method or substance to help us.
Okay, thank you for the question. Um, so how's the situation, reactive halogen situation in Hong Kong, right?
Yeah.
So actually, Professor Tao Wang at PolyU have done quite a few campaigns in Hong Kong, and they found really high concentration of reactive halogens, reactive chlorine species like ClNO2 and Cl2. So the Cl2 reach about 1 pp. It can reach up to 1 ppt, 1 ppb in Hong Kong. That's really surprisingly high. But still, the model cannot reproduce such high level of Cl2 and in Hong Kong. Okay, so we don't really understand how Cl2 is produced in Hong Kong. And while as proposed by Professor Tawang, Cl2 could be produced from, for example, nitrate photolysis induced aerosol photochemistry. But there could be also other possibility that could produce Cl2 in Hong Kong. For example, this iron-3 induced aerosol photochemistry or the ozone uptake onto the aerosols. So that's why we are really trying to understand how to do some laboratory experiments to see how how fast these reactions can produce Cl2 in the atmosphere, and then to evaluate the impacts of this formation mechanism, this new Cl2 formation mechanisms on the air quality in Hong Kong. That will be our next step as well. So the next question is how the government can what the government can do to improve the air quality in Hong Kong. Well, so in Hong Kong, so the reason why I think we have such high level of reactive chlorine species is because we have both anthropogenic and a natural source of chloride. So for example, it's a coastal city, so we have chloride from sea spray aerosol, from seesaw aerosols to mix with also the anthropogenic chloride emitted from, for example, Hong Kong, from the PRD regions, and then to react with, for example, the NOx, and then in the end to release ClNO2 and Cl2 in the atmosphere. And and this kind of anthropogenic source, maybe we can do something on it. For example, if we can reduce the chlorine emissions from coal combustion, from biomass burning, from the wastewater treatment, then well, we can improve the air quality. But again, this reactive halogen chemistry, reactive chlorine chemistry is really uncertain, not just in Hong Kong, but in the whole world. And we need to really understand really how this affect the air quality before we do anything.
Okay, thank you, Dr. Chen. So we have one question from the audience. The first question is, can we get the PowerPoint material? And then the question, can we identify or deduce the major source of HOX emission from laboratory measurement for Hong Kong, which I think Dr. Chen Dr. Chen partly answered in the previous question. But yeah. And also, one more question is about, is it possible to introduce chemical inhibitors to slow down radical chlorides to react with the atmosphere? So Dr. Chen, please.
Well, I mean, so since CO2 it's the biggest source of chlorine radicals. So if we stop CO2 emissions, I mean, if we don't have CO2 released from aerosols, then I think that it will significantly slow down the chlorine chemistry in the atmosphere. Okay, so then how can we reduce how can we reduce slow down the CO2 emission from aerosols? Well, then we need to understand how CO2 is produced again. And for example, if we have more sulfate or if we have more organics in aerosols, that could help slow down the CO2 production from aerosols. If we understand this CO2 formation mechanism properly, because now we are proposing that it's produced from iron 3 chloride aerosol photochemistry. If this is the case, then we can, of course, if we have more sulfates, if we have more organics, then these reactions will slow down. And actually, more interestingly, rather than to stop this chlorine chemistry, some scientists around the world, they're actually thinking about to inject more chlorine species into the atmosphere to remove methane, actually. So as I show you in the introduction slide, that the halogen chemistry is actually, in particular, chlorine chemistry has a net cooling effect, and that's because of the impacts on the methane. And so some scientists, they are thinking about some geoengineering projects to spray some iron and chloride containing aerosols into the atmosphere that produce a lot of CO2 in the atmosphere, and that oxidize the methane in the atmosphere. And this is some interesting geoengineering projects that we can do in the future. And this is what I'm thinking about as well.
So thank you very much for Dr. Chan's answers. So see if we have more questions coming. In the meantime, so let me talk about the CVD cert. So after the seminar, the online seminar, the CVD cert will be sent to the registered email of all the audience in due course. So I think we have no more questions from the audience. So let me thank you again for Dr. Chan's presentation, and thank you very much for the audience, for all the audience coming for the online seminar. So we hope to see all of you again very soon. So goodbye.
Thank you for your patience. And actually, for the first question, so am I supposed to upload the PPT material?
Actually, it is really up to you. So
okay, yeah, sure. So I can share the PPT if you want it. Yeah.
okay. So maybe
But I don't know how to share. Actually, this is recorded, right?
yeah, it is recorded. So maybe let's discuss after the end of the seminar and see how to give the PowerPoint to the audience.
Okay, thank you.
Okay, yeah, thank you very much.
Thank you.
Yeah, thank you all.